One way of solving a system of linear equation is called the LU decomposition or LU factorization, wherein we're going to get the equivalent lower triangular matrix and upper triangular matrix of asserted matrix. So, in this video, I'm going to show you how it's done. Say for example, you are given matrix A multiplied by an x equals b. So say for example, you are given a matrix A multiplied by x equals b, wherein A here is the coefficient matrix from that system of linear equation, and x here is the unknown vector, and b would be the constant vector. Alright, so that's the constant vector. So to solve a system of linear equation using the LU decomposition method, there are actually three methods that we can use, which are: number one, we have the Doolittle's method. Number two, we have the Kraut's method, and number three, we have the Cholesky method. So let's go over here one by one. Now, in using the Doolittle method, we are going to get the LU factorization of A, so that's equal to L multiplied by U, and the diagonal matrix or the diagonal elements of the lower triangular matrix is equal to 1. Wherein in Kraut's method, we are going to let A be equal to LU, or we're going to factor out A into its lower triangular matrix multiplied by the upper triangular matrix. However, the upper diagonal elements would be equal to 1. And for the Cholesky method, we're going to let A be equal to the lower triangular matrix multiplied by the transpose of the lower triangular matrix, or you can have it as A equal to the transpose of the upper triangular matrix multiplied by the upper triangular matrix. So, let's go over the three methods one by one. Let us now discuss the Doolittle's method of LU decomposition. So again, if we have an expression or an equation which is matrix A multiplied by x be equal to b, we can decompose the coefficient matrix into its L and U, or lower triangular matrix and upper triangular matrix respectively. So to do this one, now you might be asking, how can we solve for the value of x if we're going to solve for L and U? So if we're going to substitute L and U in the given expression here, we have L multiplied by U times x be equal to b. And if we're going to let this U multiplied by x be equal to y, we now have L multiplied by y equal to b. So in here, the unknown vector would now be equal to y. And since u multiplied by x is equal to y, we can now determine the value of x after we determined the vector y. So to illustrate how are we going to solve a system of linear equation using the LU factorization, particularly using the Doolittle's method, let us have an example here. So we have a system of three equations with three unknowns. We have x1, x2, and x3 respectively. So what we are going to do first is to create a matrix, right? So the first matrix that we're going to create would be the coefficient matrix, and the coefficient matrix would be 1, 1, 1, we have 1, 2, 2, and then we have 1, 2, and 3. The coefficient of x1 would be in the first column, the coefficient of x2 would be in the second column, and the coefficient of x3 would be in the third column. Now, it is important that you need to arrange first the given system in order. So, the first element would be x1. If there would be no second element here, you just leave it, or if there would be no coefficient for x2 here, you just leave it blank so that you will not be confused later on. So this is now multiplied by the unknown vector, which is x1, x2, and x3. And then this would be equated to the constant vector, which is 5, 6, and 8. Alright? Now, since we are going to use the Doolittle's method, again, let me just recall you with the Doolittle's method. We're going to equate, or we're going to equate A be equal to the lower triangular matrix minus the upper or we're going to decompose A to its lower triangular matrix and upper triangular matrix, wherein the diagonal elements of the lower triangular matrix be equal to 1. So, if we're going to do that, we write A, we have 1, 1, 1, we have 1, 2, 2, and then we have 1, 2, and 3. And this would now be equal to, since we do not know yet the elements of L and U, that is what we are going to find out. So this would now be equal to, since also the lower, the diagonal elements of the lower triangular matrix is equal to 1, or are equal to 1, so this would now be 0, 0, and 0. We have A, B, and C. And then this would be multiplied by the upper triangular matrix. So the upper triangular matrix, the lower diagonal elements of the upper triangular matrix would be equal to 0 as well. So this would be D, E, F, G, H, I. Alright, so let me just correct that one. We have 0, G, H, and then we have 0, 0, I. Right. Now, our objective here is to solve for the values of A, B, C until the value of I. So what we can do here is we're going to perform multiplication of matrix in here, and then we're going to equate the resulting element here to the given element of matrix A. So what I'm saying is that if we're going to multiply this lower triangular matrix with the upper triangular matrix, we would now have, so for the first element, first row multiplied by the first column. So that would be D times 1, so that's equal to D. And then 0 times 0, that's 0 also, 0 times 0. So D times 1, so that's equal to D. 0 times 0, that's equal to 0. And then 0 multiplied by 0, that's equal to 0 as well. So for the second element of the resultant matrix, we're going to multiply the first row with the second column. So if we're going to do that, we have 1 times E, so that's equal to E. And then we have 0 times G, so that's equal to 0. And then 0 times 0, that's equal to 0. Alright, so let me just put it right here. There we go. Now, for the third element, we repeat the process. We have the first, or multiplying the product of the first row with the last column. So we have 1 times F, so that's equal to F. 0 times H, so that's equal to 0, and 0 times I, that's equal to 0. So basically, the first row of the resultant matrix would be equal to the first row of the upper triangular matrix. Right. So let's continue with our computation. For the second row, for the element of the second row, first column, we multiply the second row and the first column of the upper triangular matrix. So that would now be A times D. So A times D multiplied by 1 times 0, right? So that's equal to 0, and 0 times 0. So that's basically equal to 0 as well. And then for the second element of the second row, or the second the element here, that would be the second row multiplied by this column, right? So now we have A multiplied by E plus 1 multiplied by G, so that's AP plus G, and then 0 multiplied by 0. Alright. Now, for the uh, element here, we're going to multiply the second row of the lower triangular matrix by the third column of the upper triangular matrix. So that would be A times F plus 1 times H and 0 times I. So that's basically AF plus H. And for the last one, or for the last row, we're going to multiply this row with the columns. Okay, so if we're going to determine the element here, we're going to multiply the third row with the first column. And then if we're going to get the element here, or if we're going to obtain the element here, we're going to multiply the third row with the second column, and so on. So for the element here, we have B multiplied by D, and then we have C multiplied by 0 and 1 multiplied by 0. And then if we're going to add that, that's basically equal to B times D. And for the element in here, we have B times E, so that's B times E, plus C times G, and then we have 1 times 0. So that's basically BE plus CG plus 0, or simply BE plus CG. And lastly, we have 1, or this, the third row multiplied with the third column, we have B times F plus C times H plus I. So this is now the resulting element, or this is now the resulting matrix if we're going to multiply the LU, the lower triangular matrix and the upper triangular matrix. So if we're going to equate this one to the coefficient matrix, we have 1, 1, 1, 1, 2, 2, and then 1, 2, and 3. We can already solve for D, E, and F, right? So D, E, and F is basically equal to 1, 1, 1 respectively. We have D equals 1, E equals 1, and F equals 1. Now, for the first column, right? So for the first column, we're going to use AD equal to 1 because this element corresponds to this element. So that's equal to A times D equals 1. And since D equals 1, so this would now be A times 1 equals 1, or A is basically equal to 1 as well, right? So for BD, that's equal to 1. And since D is also equal to 1, so B multiplied by 1, that's equal to 1 as well. So B is equal to 1 as well. So going further, we have AE plus G, so that's AE plus G, and that correspond to the value which is 2. Right? So A is solved to be 1, E was solved to be, or was determined to be 1 as well, plus G, and this is now equal to 2. Now 1 times 1, if we're going to transpose it on the other side, we have G equals 1. For this element, we have B, E plus C times G equals, right? So this element in here, or yes, on the right side, correspond to a value of 2 on the left side. So we now have B, which is equal to 1, E, which is equal to 1, plus letter C is actually unknown, and G was solved to be 1. So this is equal to 2. And C would now be equal to 1. Because 1 times 1, if we're going to transpose it, we have 2 minus 1, so that's basically equal to 1. And for AF plus H, this AF plus H correspond to the value 2. So this is now A, or that's equal to 1, and F is also equal to 1. H is unknown, so that's H equals 2. So 1 times 1, again, transpose it on the other side, we have H equals 1. And lastly, alright, so we have BF plus CH plus I. We now have B, which is equal to 1. F, alright, so that's, no, F is 1 as well. C is 1. H is 1. And I, alright, so that's the unknown. And this corresponds to a value which is equal to 3. Now, if we're going to add 1 times 1 plus 1 times 1, that's equal to 2. And if we're going to transpose 2 on the right side, I would be equal to 1. Now, we already know the values of A, B, C, D, E, F, G, H, and I. We can already write the lower triangular matrix and the upper triangular matrix, and then we can already solve for, right? So we can already solve for the values of x. Now, if we're going to write L, or the lower triangular matrix, so that's basically equal to 1, 0, 0, 1, 1, 0, and then 1, 1, 1. Because if we're going to look at our equation here, we have 1, 0, 0, A, 1, 0, B, C, 1. And the values of A, B, and C are 1, are all 1s. Now, for the upper triangular matrix, let me just write it down as well here. That would be DEF 0GH 00I. However, the values of D to I are also equal to 1. So we have 1, 1, 1, we have 0, 1, 0, and then 0, 0, 1. So this is now the the lower and upper triangular matrix decomposition of this matrix. Right? Now we're going to use this one to solve for the values of x. And to do that, we're going to use first Ly equals b. Now our L here is 1, 0, 0, 1, 1, 0, and then 1, 1, 1. Now our y here, we have y1, y2, and y3. And b is equal to 5, 6, and 8. So that's 5, 6, and 8. Now, we can already solve for the values of y1, y2, and y3 by multiplying this matrix with this matrix and equating it to this matrix. So how are we going to do that? Now, if we're going to test for conformity, this is 3 by 3. This is a 3 by 3 matrix, and this one, or this vector, that is actually a 3 by 1 matrix. So since the values of the number of columns of the first matrix and the number of rows of the second matrix are equal, or is equal, the resulting matrix would now be equal to 3 by 1. Right? So the resulting matrix would now be the first row multiplied by the first column of the second matrix, so that's equal to y1 plus 0 plus 0. And then the second row multiplied by this column, we have y1 plus y2. And the third row multiplied by this row, or column, I should say, y1 plus y2 plus y3. This is now equated to 5, 6, and 8. So y1 would now be equal to 5. y1 plus y2 is equal to 6. And since y1 is equal to 5, so we substitute that value, we have y2 equals 1. And lastly, y1 plus y2 plus y3 equals 8. So y1 is determined or was solved to be 5, and then y2 is equal to 1 plus y3 equals 8. 5 plus 1, it's equal to 6, and then if we're going to transpose it on the right side, we have y3 equals 2. So these are the values of y1, y2, and y3. Now we are going to use that to solve for the value of x. And x is, and solving for the value of x, we're going to use the upper triangular matrix and the vector y. So we now have 1, 1, 1, so 0, 1, 1, and then 0, 0, 1. This was the upper triangular matrix multiplied by x, x1, x2, and x3. And then this is now multiplied to y, and our y is 5, 1, and 2. Right? So by repeating the process, we now have x1. Right? So if we're going to multiply this one with this one, we have x1 plus x2 plus x3. And then multiplying this row with the column of the second matrix, we have x2 plus x3, because 0 times x1 is basically equal to 0. And for the third row, we have 0, 0, 1, so that's basically equal to x3. And this is now equal to 5, 1, and 2. Right? So the first value we can determine here is x3, which is equal to 2. And the second one would be x2 plus x3 equals 1. But since x3 is equal to 2, so x2 plus 2 equals 1, x2 equals negative 1. And for x1, we have x1 plus x2 plus x3 equal to 5. So x1 is now plus negative 1 plus x3, which is 2, equals 5. Negative 1 plus 2, so that's equal to 1. And then x1 equal to 4. So the values of x1, x2, and x3 are 4, negative 1, and positive 2. These are now the values of x1, x2, and x3.